So, guys, here with us we have Professor David Van der Spoel from Uppsala University at BMC building, and then Professor David Van der Spoel, okay, worked with force fields for a long, long time and was the main developer of Gromax package. Now it's the lead of the ACT Alexandria Chemical Toolkit, okay, a project, and is working with that, and we talk about force field science and everything behind this process, okay? So I'm so happy to have you here with us, Dave. Please, you can share your screen and talk. Thank you a lot. People, Dave, in the last lecture, we had a kind of a dynamic, okay, process here, and people could like ask and uh, put the hands up and ask you during the presentation. If you prefer that this can be like dynamic process with Q&A as Q&A process during the presentation, we can keep this, or if you prefer present first and let the Q&A at end of the presentation, also we can okay manage this. What do you think about?
I think during the presentation is fine, but then if when I'm presenting, I only see my screen. I don't see the Google. So then just
I
please
can
speak
I
up.
can help you. I can help you.
Yeah, you can chair the session basically.
Yeah, yeah.
Yeah.
I,
All
I'm
right.
the chair here, and then I can help you. Please, guys, if you have a question during the presentations, you can put your questions in the chat. I can see, and then I can ask Dave to answer and to see the chat. Or if you also want, please put your audio okay on, and then ask okay to Dave Van der Spoel. But during the presentation, please keep your audio muted, okay, to have a very good recording process. So you can share, Dave.
All right. Can you see my screen?
Yeah, I can see.
Yeah.
Good.
All right. Thank you for the introduction. And let's start. So I will talk about force field science. So we have to start by defining what is force field science. So I will start indeed by trying to explain what is a force field, what is it good for, and how accurate is it. Then I will introduce force field science and include an early example from my own lab. Then I have planned a break for a couple minutes for getting more coffee. After the break, I will introduce the
Quite
Alexandria
important.
Chemistry Toolkit. Sorry.
Now the break for coffee is quite important.
Indeed, yeah. So after the break, I will introduce the Alexandria Chemistry Toolkit and then show you some applications of force field science using the Alexandria Chemistry Toolkit. And I will end with some final words and summary. Now, if you Google for force field, you may actually find something like this, but that's not what I'm going to talk about today. So no Star Wars, unfortunately. So instead, I'm talking about force fields in chemistry. So I didn't do any cleanups yet to this page, but I could consider it. But let's highlight, so in the context of chemistry and molecular physics and so on, a force field is a computational model that is used to describe the forces between atoms or collections of atoms. And as you see here in this ethane molecule, the bond can stretch and compact. And to describe this, we need mathematically, we need to have a mathematical function that models this bond stretching accurately. Now, what is also an important issue in this definition is the word computational. And indeed, computational chemistry, and this is the Portuguese, but of course it's available in 13 more languages, Um, Computational chemistry, this is force field. Sorry. This is a computational model to describe forces between atoms. And these forces are within molecules or between molecules. So this is again this example from Wikipedia, where we show we have bonds stretching within this little molecule. So force field chemistry is like a subset of computational chemistry. And computational chemistry uses computer simulations or computers to help us to solve chemical problems. And important aspects here is that it uses methods of theoretical chemistry, which is chemistry in basically on pen and paper. The Schrödinger equation and derivations from that, and how you can model things just theoretically. And these are then implemented in computer programs to calculate the structures and properties of molecules, groups of molecules, and solids. And then in between molecules and solids, we have liquids, of course. So the goal of computational chemistry is to describe all these states of matter with a single model, in principle. Um, so, if we now want to make a model which is simpler than quantum chemistry, so we are skipping the Schrödinger equation and we want to describe our models with classical empirical potentials that we can simply write down the equations for. But what do we want to get out? So first of all, we want to have accurate energies and forces. And now accurate is a word that has been overused, one can say. So everyone pretends that their models are accurate, and quite often without giving a specific reference. Well, there is one reference that is actually somehow universal, and that is chemical accuracy, which means that energy should be within 1 kilocal per mole from experimental data. But of course, this number is nice and simple, but you should keep in mind that the energy scales with the size of the system. So if you have an energy of a molecule, a single molecule in gas phase within 1 kcal, it doesn't tell that if you model a liquid in the same way that you will have the same accuracy. Or if you have a large complex molecule like a protein. So this is still difficult to define, even though we have this chemical accuracy as a nice reference. Then we want these models to be applicable to all phases. That means gas phase, liquid phase, solid phase, maybe not the plasma phase, but this is actually not a goal that is shared by everyone. So some people in the field think it's sufficient if they can model the liquid phase. But if you think about a liquid phase, and I'm in a biology department, so people are working on proteins a lot, and protein ligand binding, for instance. If you think about that more in detail, then there is certainly one phase in the sense that the density is roughly the liquid density of water, but there are interfaces between molecules, between proteins and water, between membranes, phospholipid membranes and water, which are in principle similar to phase transitions. So even though a liquid phase would be enough for most of these things, it's not a one-phase system. So the chemistry is actually quite complicated, and therefore, if we have models that can work in all phases, that will be in our advantage in many applications.
And David, I believe this is a great challenge today, still a great challenge and we can see, for example, many force fields parameterized for one phase, like liquid phase, but even, for example, for water, where we have the anomalous, okay, phenomena occurring, it's complicated to simulate liquid in broad range of temperature. So this is a
Mm-hmm.
great challenge, is still a great challenge today. I
Yeah.
remember that paper, old paper that you published, varying different water models and testing it for many thermodynamic conditions, you remember? And
Mm-hmm.
then showing the difference between the force fields.
Yeah.
Uh, yeah.
Yeah, this is really difficult stuff to get right. It's easy to write it down, but it's difficult to get it right, that's for sure. Um, yeah, and then what's also important is that if we, let's say we model methanol and propanol, then it would be great if we can use the same model also for other alcohols that have the same chemistry. And this is not obviously the case always, but this is definitely a design goal. Then we also want to have computational efficiency, so it should be relatively fast. And then, of course, the question is, how fast should it be? Well, it should be faster than methods that are more accurate. So I mean, it should be faster than quantum chemistry, but it should be maybe doesn't have to be as fast as the simplest models if you get something in return. So there's a trade-off between computational efficiency and accuracy. And then in regard to the molecular or to the neural network potentials that Luciano mentioned in the beginning, comprehensibility, I think, is also a design goal. So if we can write down the equations and understand what they mean, that also helps us to understand the chemistry, I think. So let me just first give you an example from a paper that we published a couple of years ago. So here we looked at organic crystals, and many of those force fields that we were testing and that we were using are actually designed for the liquid state. So we said, okay, let's challenge those force fields by trying to model the crystal state. So on the left-hand side, you see a crystal of phenol. And then if we do a simulation at 123K, it looks pretty nice. If we do, it remains in the crystal form. And if we do a simulation at 350K, it forms a nice liquid. But if we are in between, what we get is actually a plastic crystal. And I wasn't aware of this before we did this work, but then we found out, of course. So a plastic crystal is where the molecules can actually move in one or two dimensions, but not in all dimensions. So in this case, you can see there are these clusters of hydrogen bonds between the alcohol groups in the phenol, and they are, of course, very strongly bound, but the molecule can actually rotate around its axis. So this is something that we discovered, and we found this actually in quite a few crystals. And what we also found is, and I will come back to that, is that the models that we used are not super accurate for the crystalline state. And that is actually the topic of this slide as well. So how accurate are current force fields? Well, we need to test them in gas phase, liquid phase, and solid phase, evaluate as many properties as we can, and compare to experiment. So far, so good. So let's look at some examples. Here is a bunch of papers that we published on this stuff. I'm just highlighting one, which is a review. So if you want to learn more, then please go to this DOI and download the paper. And on the right, you see an artist impression of a polymer of this kind of molecules that we studied in this in this paper. So let's look at some more details. So here's an old paper where actually Luciana was also one of the co-authors, where we looked at 150 liquids, organic liquids, and looked at their properties. So here we have the surface tension from experiment, and on the y-axis calculated using either of two force fields, GAF or OPLS AA. And what you see is that many of those surface tensions are lower than experiment. So the black line is perfect matching, and most of these are actually lower. And one of the reasons for this is the use of cutoffs, so that we don't take all interactions into account. So that can be compensated for to a little bit. And then here on the right side, we have the dielectric constant experiment on the x-axis and calculation on the y-axis. And you see also that these are almost all are underestimated. And what's more, that we have a logarithmic axis here. So these are underestimated a lot, actually. So this is a very difficult property to get right, because it has to do with the electrostatic interactions at long range, the motions of the molecules, and so everything is playing a role. If molecules rotate too fast, you will get too high dielectric constant, because they provide more electrostatic screening. And if they rotate too slowly, you will have a too low dielectric constant. More examples. Here are free energy of hydration, or free energies of solvation, I should say, where we have around a few hundred numbers, experiment on the x-axis and calculations on the y-axis. And on the right-hand side, we have the same data, but then in the residual plot. I typically like residual plots better, because you can see much better how good the results really are. So the black dots above here are from force field calculations. And you see they are quite noisy with large RMSD. And see the red and the green are empirical models. This is completely empirical. And this is Cosmo is based on some form of quantum chemistry. But you see that they are all of similar quality. So not great. Then we moved on to gas phase thermochemistry. So we're just looking at vibrations in molecules and looking at, in this case, heat capacities. And you see also that these plots are very, very noisy compared to the references here now, quantum chemistry. So vibrations are not described well either by existing force fields. And then back to those crystals. So here we have around 30 or so, 35 organic crystals for which we calculated the density. And you see the spread is also quite large, even though it's pretty close to the y equals x line. But still the RMSDs are like 80 kilogram per cubic meter, so 70, 80. So we're talking 5-6%. And the same goes for the enthalpy of sublimation for those same crystals. So they are in the right ballpark, but the numbers are still rather noisy. And there are some outliers like here, where you're really quite a bit below the energy. So it's really difficult to make good predictions, and we're still quite far away. So from 1 kcal per mole accuracy for these energies anyway. And if you look at the number of properties and look at the average error, you see that it depends a bit on what property you're looking at, but the errors vary from a few percent to 15-20%, depending on what you're looking at. And also the correlation is pretty high for some things like the density, but for more difficult things like compressibility, this is quite a bit lower. And that means that the density may be quite okay at room temperature, but if the compressibility is not okay, that means that the temperature dependence is also um, not very good. All right, so let's move on to force field science. So the term comes from a paper by the Open Force Field Group, led by David Mobley, Michael Church, Mike Gilson, and others, where they describe the progress in their force field project. So it can be defined as the study of the impacts on force field accuracy, transferability, computational cost, etc., of things like potential functions, charge models, and also parameterization strategies. So if we change the potential function, how much more or less accurate does our force field become, and how much more transferable, and also not to be neglected, how much more expensive does it become? But interestingly, while they define this term of force field science, they also describe it as an arduous task involving a lot of human efforts to the point of being impossible. And they call it a nearly unexplored branch of computational chemistry. So that was very nice for them to make such descriptions, because then it shows that we can actually contribute something. But before we get into like these kind of details, I would take you back on a literature study to 1969, and that's a long time ago. It's more than 50 years ago, but the writer of this paper that I'm going to show you is still with us, happily. This is a paper by Michael Levitt, Refinement of Protein Conformations Using a Macromolecular Energy Minimization Procedure. And at the time he was with Schneider Lifson in Weizmann Institute, I think. And in this paper they write that the total molecular potential energy is composed of many terms. Its exact form is unknown, and the expression used in the present calculations is a gross approximation. And this is the equation that they have. And if you have studied any force field calculations, you recognize the harmonic bond potential, harmonic angle potential, dihedral torsion potential, Van der Waals Lennard-Jones potential. They did not include a Coulomb interaction, interestingly, but they have like a restraining potential. And of course, the author of this paper got the Nobel Prize in 2013, Michael Levitt, for the development of multi-scale models for complex chemical systems. But talking to my colleague who is in the Nobel Committee, this paper that I just showed could actually also have been sufficient reason to give it to him alone. But yeah, this is not how it went, but that's an interesting side thing to know. Okay, so we have looked at the literature in 1969, and Michaels wrote that.
They've
Yeah.
just a curiosity about that. The guy that he told you this, okay, was uh, Yorkvist.
Åkvist, yeah, yeah,
Yeah,
yeah.
good.
So what they wrote in this paper is that the total molecular potential energy is composed of many terms, its exact form is unknown, and the expression used is a gross approximation. 1969, right? Okay, fast forward to 2020, where a group of people wrote about force field for molecular simulation. One of the major challenges of molecular simulation is the specification of the interparticle interaction potentials, both in terms of the functional shape and the respective parameter values. So basically, they say exactly the same thing as Michael Levitt 50 years earlier. So one could think that we haven't learned so much during those 50 years. It's not that bad, but actually many of the well-known force fields, they stick to this with to a large extent to these equations that Michael Levitt had in his paper already then in '69. Okay, what do we need to perform force field science? So first of all, we need comprehensive data sets that cover the chemistry that we're interested in, that are large enough to sample, for instance, different conformations of molecules and have accurate reference numbers. Then we need a software to rapidly train a complete force field. And then we use the same data for all training and testing. So I'm referring here to a review paper by Arne Hagler, who writes in a very nice way about these things. That is actually he's not so nice to all the people in the field that group A makes a model for proteins and group B makes a model for RNAs, and then they try to combine the things, but then of course these things are not compatible because they have different data sets, different training sets, and we cannot match them. But then even if we start to match things and retrain things, then the data sets shift all the time, such that if we make a new version of a model, people test it on a new data set, and then we do not know how well the new model works with the old data set. And in the end, development in this way is running in circles. And Hagler writes about people making fixes to models in the wrong way. So they fix a problem in the engine of the model by changing the seats of the car or something like that. So it's important to use the same data if you're comparing apples to apples, basically, and not apples to some oranges or something else. And then, of course, validation is really important. In the end, if we train on quantum mechanical data, we still need to validate on experiments because it's not sufficient to be able to reproduce quantum mechanics. So here's an early example of force field science from my group where we made a model for alkali halides that worked both in the gas phase, in the liquid phase, and in the solid phase. There are hugely different temperatures. So if you think about sodium chloride, for instance, it forms a nice crystal and it melts around 600-700 K, if I remember correctly. And then, of course, the surrounding of all the atoms changes a little bit. Density changes quite a bit. And in the gas phase, you typically have ion pairs, which can vibrate. And so if we have one model that can do all that, that would be great. And actually, this kind of molecules or compounds is actually used quite a lot in, for instance, energy. There is a model for a nuclear reactor, which is called a molten salt reactor, where a fissile material is cooled by having it in a bath of molten salts. And molten salts are also used for energy storage. So there's a big plant in Morocco where they have parabolical mirrors mirroring the sun rays onto a big tower filled with molten salts. And so they heat this up during the day and then they can extract energy during the night. So these are actually quite interesting compounds in that respect. So what we did, we made this model consist of each particle consists of a core with a positive charge, and a shell, which is a polarizable particle attached to it with a negative charge. And in this model, both of these have the same distribution width for the Gaussian. And we trained the same model with the same data on 4 different van der Waals potentials. So this is where the force field science comes in. We change one thing at a time, so we have fixed the electrostatics, and then we change the van der Waals potentials, and then we can compare. So we need to model Coulomb interactions and van der Waals interactions. We have experimental data for ion pairs in the gas phase, distance, dissociation energy, and dipole. So I want to try and involve the audience a little bit. So I was going to ask you, how can we use such data? So I'm going to quit my, I'll stop the presentation for a sec. So if we have experimental data like ion pairs in the gas phase, data, distance,
Okay,
and
I don't know. I don't know what happened, but your screen is not showing the slides now.
yeah,
Something happened.
it's either all or nothing. So I just moved it away so that I can interact with the audience if anyone is feeling
Ah,
like
okay.
they want to
Okay.
answer a question. Um, so we have, let's say, sodium chloride. We know from the experiment the dissociation energy. We know the distance where they are. We also know the dipole of the sodium chloride in the gas phase. How can we use that data? Maybe the question is too difficult if you're not prepared. Okay, no one is saying something, so I will just continue. But please, if you have questions, then let me know, of course.
Hey guys, do you have questions to Daft, please? Se tiverem questões, podem fazer também em português. Eu posso ajudá-los aqui no chat, tá bom? É só escrever aqui no chat, a gente pode passar essas perguntas para ele, né? So, don't be shy, okay? Please share the questions, okay? Good. Please go ahead,
Yeah.
Dave.
Okay, so an interesting thing, if you look at these things in some more detail, is that the distance in between ions and if we know the distance between the ions and the dipole from experiments, so we have here for different ion pairs, lithium fluoride, sodium, and so on, the distance for those ions in the gas phase. We also know their dipole moment in the gas
Yeah,
phase,
Daft,
and this.
we have a comment in the chat. Can you see?
No,
Or
sorry,
no. Alexandre, okay, PhD student here wrote. Basically, that's the information that describe the non-bounded interactions, right? Yeah.
Yeah, that's correct. Yeah, to some extent, though. So let's look a bit more at this data. So what we have here is the experimental dipole. But if you would to put 2 point charges, so the simplest possible model, like a +1 and a -1, at the same distance, you would actually get a much larger dipole. And this actually goes for all of these compounds, that if you take 2 point charges at a certain distance, corresponding to the experimental gas phase distance, then the dipole is overestimated. And you can just take the ratio of the experimental and the theoretical one, and you see that it is something like 60 to 80% for most of these. So what does this mean? Well, it means that we have charge penetration. So the charge clouds overlap between these atoms or ions in the gas phase. And now if we replace our point charges by these Gaussian charges that I told, then the interaction will become weaker at short distance. And actually with our models, we are able to, with these Gaussian models, we can describe this much better. So we can adapt those Gaussians to reproduce this dipole of the molecules. And once we have done that, so we have the charges and the Gaussian width that give us the experimental or very close to the experimental dipole, we can also calculate the electrostatic energy between those two particles. And then what Alexandre said, we get information on the non-bonded. Yes, that's correct. We get information about the electrostatics here, but then we have to add the van der Waals interactions. And that if we know the dissociation energy and the electrostatic energy that we derive from this, we can then also model the van der Waals energy. And these are what those kind
Yes,
of distributions
Dave,
look like.
yeah, Dave, before talking about these distributed chart models and going back to the van der Waals functions that you need to add, yeah, together
Mm-hmm.
with this treatment, from the literature, we can see many different, okay, van der Waals functions to modeling the molecules in the system. So we have the traditional Lennard-Jones potential to describe that, but also we have others like
Mm-hmm.
Buckingham and so on. And uh, depending on the ionic systems that we are uh, trying to simulate, it's quite challenging, for example, to simulate it or like reproduce the solid phase using the Lennard-Jones potential, for example.
Mm-hmm.
Uh, so can you comment a little bit your experience using different, okay, van der Waals potentials to describe better the molecules, okay, in the system, please?
Yes, absolutely. Actually, I was did this so in this particular paper, we tested 4 different van der Waals interactions. So I will come to that in a couple slides and also in the second half of the presentation.
Nice, good, good.
Yeah, so just to remind you that we have 2 popular ways of distributing charges. So first is using a Gaussian function, which has this equation, and then second using a Slater function. And the Slater function is famous, of course, for being the analytical solution of the Schrödinger equation for the hydrogen atom. And it's also, sorry, it is usually slightly more accurate than this, but it's also more expensive to calculate. So we stuck to Gaussians anyway. And then to exemplify, so we have, in this case now, a molecule, but we have these core particles with a positive charge, and then we have a shell particle which can move away from the core that has this Gaussian charge. And this particular model, they both have the same Gaussian charge. Right, that's what I just said. And then we used Wang Buckingham, normal Buckingham, Lennard-Jones 12.6 or Lennard-Jones 8.6 potentials, and identical training for everything. We're training on the gas phase data, dipoles, dissociation energy, but also on the solid phase. Then if we look at a number of different properties, density, temperatures for, let's see, the density in the liquid phase and density in the solid phase, but also gas phase properties, we can see that the average deviation, root mean square deviation in percent, because we have different properties that we are comparing, for published models was around 12% if we train everything ourselves to a 12.6 Lennard-Jones potential. the average RMSD was 7%. And if we use this Buckingham variant, which is like a potential with 3 parameters, the error drops to 3%. And the other two, Buckingham and H6, are like in between. So here we have like 4 different Van der Waals potentials, and we train everything in the same way, and we see how much a more expensive but also more accurate potential gives us. It's like twice as good as this one.
Is this average for all those ionic systems that you showed before in the table? Okay.
Yeah, so we have 20 alkali halides,
Okay.
and you should actually also remember that they all but 3 of those have a sodium chloride, like square crystal,
Yeah.
but cesium chloride, bromide, and iodide have a different crystal form as well. But we are able to model those as well with these models. So 20 different alkali halides, and then these, I think, are 7 or 8 properties or so that were for which we calculate the RMSD.
Yeah. One comment, I guess, this is interesting to say. The Drude polarizable model, okay, is a little bit expensive when you compare it with the, for example, one Buchan potential. So, or the way that you treat the distribution, the chart distributions using the Gaussian oscillator distribution. So I believe if you use Drude's polarizable model, okay, the computational cost, okay, will be higher when,
No,
okay,
sorry, I
yes,
didn't
or
say
not.
clearly, but these models are also polarizable. So that's basically
No,
they are.
yeah. The vowels on one Buckingham is polarizable from the distributed chart. A Drude polarizable, in terms of the computational cost, okay, is higher than these ones, okay, in
No,
terms
so
of the
no,
computational cost.
this one is all basically both charm and this guy are like 12.6 with polarization, so they should be similar, but this is slightly more expensive due to the Wang
Oh, the last
Buckingham.
one is more expensive
Yeah,
than the
yeah,
Drude polarizable.
yeah,
Okay.
yeah.
How much in terms of order of magnitude?
As so comparing this to this, it should not be maybe 10-20% or so.
Okay.
Uh, but this is of course much faster because it's not polarizable, de Jong and Cheatham.
Not yeah, of course.
Yeah. All right, so then we took this model and we did a couple of applications with it. And so here's one where we actually looked at the melting point. And so typically phase transitions are like really difficult to model, but I think we did okay here. So the black line is experiment, and then on the x-axis you have all the different salts, first lithium salts, sodium, and so on. And then on the y-axis is the temperature of the melting point. And you see that we now, in principle, have one model that should describe everything. And the melting temperatures, they vary from 700 or so to more than 1200. So it's quite difficult. And this JC, non-polarizable model, you see it's like way off. It's way too stable. So all the numbers are way above the experimental numbers. And then here's another model from the literature, which is then rather too low for some of them, although it's not super bad, but particularly for fluoride, it's too low. And then in the stars are our best model, which give an RMSD of like 70, 80 Kelvin compared to 250 for the non-polarizable model. So the melting point is like 3 times more accurate than for the non-polarizable model. Of course, it's more expensive, but then you get something in return as well. And here's another some data for another paper where we looked at conductivities. So these molten salts are also of interest in for battery systems. So to model battery systems, the most important property is their conductivity, so how much charge it can transport. And here you see that again for this is JC is again Young and Cheatham, the non-polarizable model. WBK, Wang Buckingham is our model, and this is experiment. And for these mixtures, basically the non-polarizable model is way too sticky, so the interactions are too strong, and therefore the conductivity is like way too low, and we are actually pretty close to experiment. So by making these models better and doing it systematically, we are able to get better results closer to experiment, and therefore I think we can make better predictions. Yeah, so I think I will skip the discussion here. It would be much nicer if I was there in person. It would be much easier. But so, what does an atom look like? Well, it's not a point charge. It's the model that I described just now had a Gaussian core with a positive charge and a Gaussian shell with a negative charge. But this is actually not a really good description of an atom. Actually, what is a better description is what is used in quantum mechanics, a combination of a point charge and orbitals or electron density and DFT. So in the simplest form that we have used recently, we combine a point charge with a Gaussian charge on top of each other. And if we look back at alkali halides, let's look at some electrostatic potentials that we can calculate from quantum mechanics. So the electrostatic potential is a function of distance from the atom. So if we say that we are probing the electrostatic potential at Ri, then we have to take an integral in 3 dimensions of the quantum mechanical charge distribution, including the core and all the electron cloud over all space. And if we do that, we get the following kind of curves. So on the x-axis we have distance from an ion. We look again at anions and cations, and for reference we also have a negative and positive point charge. So if you start here at the anions, if we have a negative point charge at 3 angstrom, then the electrostatic potential is something like this, minus 600 or so. The math is quite easy. Now, if you go closer and closer, then the negative point charge will, the electrostatic potential will go to minus infinity. However, this is not what happens in reality. If we take, for instance, bromide, which is the largest of those 3 ions, then we see that at short range, actually the electrostatic potential becomes positive. And the reason for this is that if you have the core of the atom and you have a large electron cloud around it, if you come too close to the core, you will actually feel the core much more than you feel the electron cloud, which is already outside of you. And therefore, the electrostatic potential for those ions actually changes sign. In particular for bromide and chloride, and for fluoride you have to go even closer for it to change sign. So that means that the point charge is not only quantitatively, but also qualitatively an incorrect model of the electrostatic potential generated by such a particle. And we see the same here for the cations, although the effect is much less, because this is always repulsive, but it becomes more repulsive for potassium, which is the largest of these 3. And if you get close to the potassium core, then and you come like within the electron cloud, then the potential will become much more positive than that of a point charge. So this shows us that point charges are not a good model to describe like electrostatic interactions. And of course, ions are the most strongest interacting particles, but I think it will also go for like carboxylic oxygens. But we are still working on these kind of things. So let me just summarize this first part. Force fields are analytical models of intra and intermolecular energy. The accuracy of simple models depends on the property of study. As I showed that, for instance, density is quite well modeled by current force fields, but compressibility and these kind of things, not so much. Difficult areas in particular include phase transition and temperature dependence. And the aim of the force field science is to do apples to apples comparisons of force fields and change one thing at a time and then evaluate the results. And we showed that the Wang-Buckingham potential, for instance, yields models that are much more accurate than Lennard-Jones. And the charge model used for the alkali halides that I just showed was challenged in later work. So I will come back to that after the break to show how we can improve on this model that just has two Gaussians.